Professor Clements with you as we continue talking about the nucleus. If you're using OpenStax College Physics, they're in Chapter 30, and want to talk today about the structure of the nucleus. This is really a continuation of previous, Chapter 31. This is a previous video continuation, talking about Section 3 and Section 4 of Chapter 31 of OpenStax College Physics. We see some materials here. We have a lump of coal. There's carbon-12 in there that's stable. We'll talk about those notations. We have a disk that has some uranium in it that's unstable, that decays billions of years, the half-life. And we have some cesium that's radioactive with a shorter half-life. So carbon, uranium, cesium, these nuclei behave in different ways, and we want to try to understand how that behavior is different and what are the radiations, the alpha, beta, gamma radiations that leave these materials. So structure of the nucleus started to develop in the early 1900s. We have Rutherford giving us an idea that there is this isolated positive charge in the nucleus. Rutherford first gave us the nucleus concept, but later experiments with collisions of alpha particles and nitrogen, it was observed that a positive particle, very massive compared to the electron, this positive particle is ejected, and so that became named the proton. And the proton is roughly 2,000 times the mass of the electron. It's significantly more mass. Then further on the structure of the nucleus, other scattering experiments showed that neutrons could be ejected from the nucleus, the neutron having no net charge and having a mass about equal to the mass of the proton. So those are the two objects that are found in the nucleus, the proton and the neutron. Again, our diameter of the nucleus about 10 to the minus 15 meters. Diameter of the atom about 10 to the minus 10 meters. So we're on a much different scale than the atom, much smaller. Here's an artist's conception of a nucleus, protons in blue, neutrons in green, and maybe not quite accurate in that the protons look like they're touching. Neutrons look like they're touching, but we don't have any images of separate protons and neutrons. We don't have any images of the nucleus. We can image the whole electron cloud of the atom, but definitely have protons and neutrons as constituent members inside our nucleus. So in going on with this and talking about isotopes, the hydrogen, normal hydrogen, the most abundant form of hydrogen, just has a single proton in the nucleus. If we have a proton and a neutron, it is still hydrogen. Chemically, it's still hydrogen. One proton will have one electron. The chart or the diagrams we're looking at here are ions. The H+, the plus means the electron's been taken away. So we're just looking at the nucleus here of the hydrogen, but it's deuterium, and we've got a different language going on here on this slide, but it has good illustrations. So H2, when we have, and this is not the molecule H2, but 2 denoting how many nucleons are in the hydrogen. 1 proton, 2 nucleons. And then tritium is an isotope of hydrogen where there are 2 neutrons and 1 proton. It's radioactive, but 1 proton still, so there's going to be 1 electron, but now there are 3 nucleons. Isotopes of an element, we have a constant count on the number of protons. So chemically, they're all the same, but we have a different count of neutrons, and that gives us the isotope. Another example of isotopes with oxygen, nitrogen, and carbon being illustrated here. Carbon, all isotopes of carbon have 6 protons. All isotopes of nitrogen have 7 protons. All isotopes of oxygen have 8 protons. And there are other isotopes of these elements that aren't shown here, but let's just pick on this nitrogen. How many neutrons in this nitrogen? there are 7 protons, there are 15 count of objects, nucleons, in the nucleus. That includes protons and neutrons. So if we use up 7 of this 15 number just with protons, and there are 8 remaining, this isotope has 8 neutrons. For the oxygen 18, there are 8 protons, there are 10 neutrons. So this top superscript number gives us the count of nucleons, protons plus neutrons. The bottom number is the number of protons, and this is a little bit repetitive. Just the chemical symbol would inform you on the number of protons that are there. You might have to go to a reference source to find it, but you don't technically need the sub 8. So the size of the nucleus. Again, these scattering experiments can be used to infer the size of the nucleus and how the bombarding objects are deflected. The pattern of their deflection gives an indication of the size of the nucleus. And in this notation, the important consideration for the size is the A value, the atomic mass number. Is a count of the number of nucleons. Again, we get that from Z, the number of protons, plus N, the number of neutrons. This is not the small n of quantum mechanics. This is the count, capital N, the count of the number of neutrons. So carbon 14 as an example, 14 for the nucleons, 6 for the protons because it's carbon. How many neutrons would there be? And you should answer 8. 8 neutrons, 6 protons would make 14 nucleons. So the scattering experiments, we have an approximate formula. This is, the nuclei are not necessarily perfect spheres, but the scattering experiment gives us a rough measure of the radius of the nucleus. 1.2 times 10 to the 15 multiplied by the A value to the 1/3 power. And that gives us a number of meters. So in doing this calculation, you would find the A number, this superscript, put that in, use your calculator to take a cube root, then multiply that result by 1.2. And this formula, it possibly would click something with the volume of a sphere. The volume is 4/3 pi r cubed, and the volume is roughly made up by the number of nucleons that are present. So the volume 4/3 pi r cubed, if we want to solve for r, that means taking a cube root of the count of the number of objects and the scale factor, kind of how big they are. That's a rough motivation for this calculation. But you find the superscript number, for example 243, you take a cube root. Or boron, this 9 is the atomic mass number. You take a cube root of that. But let's suppose we just wanted, without doing any calculations, real exact calculations, we want to compare the radius of 243 uranium, this particular isotope, to boron 9, that particular isotope. What would you guess? How much bigger is the uranium than the boron? What do you think that value would be? Well, you might try dividing here. The 243 divided by 9. I could take the 9 in here twice into the 24. That would leave 18. Give us an 18. Subtract from 24, that's a 6. Carry down the 3, 63. Divide 9 into 63, I get a 7. So 243 divided by 9 would be 27. This A number is 27 times bigger. The radius goes as A to the cube root. And the cube root of 27 is what number? 3. 3 times 3 times 3 gives us 27. So this uranium nucleus is 3 times larger than the boron nucleus. It's kind of amazing. There's not much change in the size of the nuclei across the periodic table. Uranium is near the end of the periodic table. Boron is close to the front. But the A numbers differ by a factor of 27. The size only differs by a factor of 3 because of this cube root factor. Okay, taking a look at the nucleides, the different isotopes that are present, and plotting this with the proton count, the capital Z on the horizontal axis. So uranium is out here at 92, the boron is back here at 5. The number of neutrons on the vertical scale. And the pink here, sort of the solid pink, roughly, this is the region of stable nuclei. They're not radioactive. Above and below this region of stability, the nuclei are radioactive. They're unstable. And then there's an endpoint up here. Above lead, all the isotopes are radioactive. But notice that it's above this line n equals z, this straight line n equals z. And I've got another version of this to take a look at, where the half-life is being shown here. The black indicates the stable nuclei. There's just a scattering of boxes. There are a lot more radioactive nuclei than there are stable nuclei. But the black is our stable nuclei. Again, this line of the number of neutrons equal to number of protons is right here. And we find that as we go up the periodic table, to be stable, it requires a surplus of neutrons. We need more and more neutrons to get a stable isotope. Again, the half-life showing here, very long half-lives are in the dark colors, the red, and the very short half-lives, isotopes that don't last very long, are the blues and the very light blue. So this was something that physicists have to explain. Why is it that the stable nuclei, we need more neutrons than protons? Why would that be the case? Well, let's think about carbon. For carbon, there are 6 protons and 6 neutrons in the most abundant isotope, carbon-12, 12 nucleons altogether. The nucleus is very small, okay, this order of 10 to the minus 15 meters. Protons have positive charge. We're putting these objects very close together. This R is 10 to the minus 15. The Q's are small also, 10 to the minus 19. But if you would calculate the acceleration, I'm not going to bother to do it here, but the electric force is kqq over r squared. If you would calculate the acceleration using F equals ma, the mass of the proton is very small, and you'll get a tremendous value for the acceleration. Why is it that protons stay near other protons in the nucleus? Why do we have any stable nuclei at all? Why do I have any atoms at all, other than just hydrogen? So this goes to this question down here. The stable nuclei have a surplus of neutrons. As we get more and more protons in the nucleus, we get more and more repelling force. And that repelling force is a long-range force. It's a long-range force. It exists all the way across the diameter of the nucleus. So they're repelling, but they're staying together. Is there another force present? And that answer is yes. There's something called the StrongNuclear Force. It's called the strong force because it's stronger than the electrical force. It's stronger than the repelling force. However, it's different than the electrical force. If we get back someplace, we had, now I've lost track of where it is, but the Coulomb Law Force is probably actually coming up right here. So the Coulomb Law Force, we have these protons that are repelling each other, and the force decreases a little bit as you go across the diameter of the nucleus, but not much. There's a lot of repelling force. What keeps the protons next to each other? The strong nuclear force. It's stronger than the Coulomb's Law Force. It's stronger than repelling. It keeps the protons together, but only across a limited span of distance. On the order of 10 to the minus 15 meters, maybe a little less. So the strong nuclear force does not apply to protons that are across a large nucleus on the opposite ends of a diameter. That proton would not attract the other proton. The strong nuclear force, protons attract protons, protons attract neutrons, neutrons attract neutrons. And neutrons become kind of a glue. Up here in the higher part of the periodic table, these protons, many protons, 60 protons in a nucleus, all trying to repel each other. The neutrons that are here, and more neutrons than protons, the neutrons act like a glue. There's strong nuclear force between protons and neutrons, neutrons and neutrons, and that strong nuclear force is what keeps the protons together. We need more glue because the nuclear force is short range. The nuclear force does not extend all the way across the diameter of whatever atom this is. It has Z of 60 across the diameter of the nucleus. So the protons are still repelling each other on the opposite ends of this nucleus diameter, but the strong nuclear force is not active between the two protons across the diameter of the nucleus. However, the interior protons and neutrons, especially neutrons helping, provide force, attractive force, that keeps everything linked together, kind of like a chain. So we do have a stable nucleus if we have this surplus of neutrons. So radioactive decay. Radioactive decay. There are two principles to be employed here when we look at an equation of radioactive decay. First, we must conserve the charge. So down here, radium, 88 protons. Here, radon, 86 protons. Alpha particle, 2 protons. This charge of plus 88 in the nucleus is accounted for over here. There's a sum of 88 plus charges over on the right side. We must conserve charge in every reaction. Then the number of nucleons is conserved, the count of protons and neutrons. So starting with 224, later we have 220 nucleons here and 4 nucleons in the alpha particle. So we're conserving the bottom numbers, we're conserving the top numbers. 224 equals 220 plus 4. 88 equals 86 plus 2. Conserving charge, conserving number of nucleons. However, the total mass of the nucleus is not conserved in this decay. In this decay, this parent, radium, decays into a daughter, radon, and then there's an alpha radiation that comes off. And in this process, there's less mass afterwards. There's more mass before in the parent nucleus. We measure mass conveniently for nuclei using atomic mass units, the U symbol. And you can look up the number of kilograms in your charts, but the U's are convenient. Kilograms are not convenient. We'd always be putting in a 10 to the minus 27 or something for the mass. So the radium, 224.020212, it's a fairly accurate measurement. That's the atomic mass units. The radon and the alpha particle, if we sum up their masses, we get 224.01, 3997. If you subtract these two numbers, the radium minus its total mass afterwards, you find that 0.006215 U's have disappeared. They've been converted to energy, and we can find that energy using a conversion factor, 931.5 MeVs per U. And multiplying that, you should check this. I came up with 5.79 MeVs. There's conservation momentum as the alpha particle goes out from this intermediate nucleus here. As the alpha particle flies off, conservation momentum. This has the small mass, it has the larger velocity, it has almost all the kinetic energy. So we're not going to consider the recoil of the radon gas nucleus. So alpha particle roughly has 5.79 MeVs. And that's what we've talked about before. Nuclear radiations have MeVs type of energies. So here's kind of a broad view. The parent nucleus, alpha particle decay happens for large nuclei. And it's thought that the alpha particle actually can be kind of a constituency inside the nucleus. And so you have alpha particles, not totally separate, just protons and neutrons, but alpha particle packages. That the alpha particle comes out, and we have a daughter product remaining. Less mass here afterwards, more mass, what we had before, and there's energy released in this process. The alpha particle carries out kinetic energy. There's a very interesting feature of how the alpha particle escapes that we'll talk about later in this chapter. So Enrico Fermi, a very leading physicist regarding the nucleus, both doing experiments and with theories. So there's a whole list of items here. He was also the leader of the project developing the atomic bomb and the first controlled nuclear chain reaction. We'll talk about that in the next chapter with nuclear power. So beta decay. So beta decay, and the normal beta decay is beta minus decay. We have some parent nucleus before, and we have a daughter nucleus after. And this happens for all across the periodic table, not just the heavy elements. So the daughter product, the electron, was observed coming out early on from radioactive decay. This is the beta particle. But when this was measured, it was found the energy was not conserved and momentum was not conserved for this reaction. Would you think that is strange, that momentum is not conserved and energy is not conserved? You should say yes. Those are prime conservation laws of physics. The way it was made to be conserved, both of those, was to make a hypothesis that there was this particle called the neutrino, and actually this is an anti-neutrino. We'll talk about antimatter in the future, but it's an antimatter neutrino that comes out of the electron, carrying off energy and momentum and rebalancing things so that conservation momentum and energy is consistent, is true here. So the neutrino hypothesized in the 1930s, detected in 1956. They're very difficult to detect, but technology did advance, and by 1956 they could be measured, and this beta reaction confirmed. The other type of beta decay is the positron decay, beta plus, positron, and coming out of the nucleus, a positron and a regular neutrino. This has an important medical application for scanning. Then a decay series. We start with uranium. Uranium is radioactive, and there's a sequence of decays here. Anything coming off in the red line down and to the left, that is an alpha decay. And then things, these little blue lines coming off to the right, those are beta decays. But taking us through a sequence of elements, uranium to thorium, radium, radon, polonium, lead, there's radioactive isotopes lead, and then eventually more alphas and betas, and we get to a stable isotope of lead down here. But a decay series, and you can see the half-lives, 4.5 times 10 to the 9th billion years. That's roughly the age of the Earth, the solar system, asteroids, planets, and so forth. And this becomes important. We talk about half-lives and doing radioactive dating. So decay series. Then gamma decay, our third decay. Again, we have to conserve charge and we have to conserve number of nucleons. It's easy for the gamma decay. So here's potassium-40 with a star on it. That tells us it's excited. The nucleus has extra energy. And it decays, leaving us with potassium-40. Nothing's changed for the counter protons or counter neutrons, but the extra energy now becomes a gamma ray. 0 for the proton-neutron count in the gamma, 0 for the charge. It is light. It's a photon. So the gamma decay is the easiest of all the ones to process. We don't change the A number or the Z number, but we do take energy and becomes the gamma ray. And it's thought that what's happened here is the proton and neutron have gone through energy level shifts in a very similar way to what happens to electrons around an atom to emit visible light. But here we have a much stronger force present, the nuclear force, much more energetic, high energy levels in the nucleus. And when the proton or neutron makes a transition, we get a much more powerful photon, more energetic light coming out of the nucleus. So gamma decay. And Maria Geppert-Mayer was instrumental in putting this shell model together, these energy levels of protons and neutrons. So that's our start of really just kind of halfway through this chapter of taking a look at radioactivity in just a little bit more detail. So we've examined the concept of the nucleon, the protons and the neutrons, the radius of the nucleus, about 10 to the minus 15 meters, very dense material. The atoms are less dense because there's empty space essentially between the nucleus and the electron cloud. But we have very dense material. We have the stable isotopes where there's more neutrons than protons. The strong nuclear force is keeping the protons together. It's stronger than the electrical force, but it's short range. So on the larger nuclei, we need a surplus of neutrons to act like links in a chain to hold the two sides of the nucleus together. We can have radioactive decay if we have too many neutrons in the nucleus, if we have too few neutrons. But the stable ones have just right, a little surplus of neutrons. We can calculate the energy of the emissions that come out, taking into account the masses of the isotopes before and after, using E equals mc squared with a convenient conversion factor, 931.5 MeVs per U, per atomic mass unit. We conserve charge, we conserve atomic mass number in the equations. And we have beta decay in two forms, an electron coming out for the normal beta decay, or a positron coming out of the nucleus for the positron decay. And then the gamma decay indicates that the protons and electrons have energy levels inside the nucleus. So review that, keep reading, keep asking questions.